Okay, so in this video, we're essentially continuing a conversation we've had from other topics. So I've titled it Power Series Computations, but it really is just a continuation of things that we've talked about earlier. What we're going to do now is we're going to use these Power Series expansions in order for us to be able to more easily integrate, take limits, differentiate, whatever you need. And so this is something that you'll encounter from time to time in differential equations as well. Being able to use these Power Series in order to make simpler concepts even simpler to compute. We've got the integral, the definite integral from 0 to 1, and then we've got our function dx. And so I'm going to go ahead and rewrite using our expansion for cosine that we came up in an earlier video, which was 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And again, go out as far as you need to. If you're not sure, just go out a few extra terms and you'll be okay. That's going to be over x squared dx. And now, when we go ahead and distribute the negative, so all of these signs will change, you'll also see that the 1 and negative 1 will do away with each other. So in writing that out, that's going to give me now an x squared over 2 factorial minus an x to the 4th over 4 factorial plus x to the 6th over 6 factorial minus x to the 8th over 8 factorial. And that's still divided by x squared dx. And so one more step, and I think it's going to be a pretty simple integration. That's going to give me a 1 over 2 factorial. So what I'm doing now is I'm taking this guy and dividing it up into each of these terms here. Then I'll have a minus x squared over 4 factorial plus x to the 4th over 6 factorial minus x to the 6th over 8 factorial. And then once again, don't forget that dx there. Okay, so now once we go ahead and we integrate, this first term is going to be 1 over 2 times the x, so 1/2 x. And then minus, this is going to be an x cubed, and then so we added 1. If we divide, that's going to be a 3 times 4 factorial. Then plus, add 1, so we have x to the 5th, and divide 5 times 6 factorial. And then minus, add 1 and divide, and that's going to be a 7 times 8 factorial. And again, this would continue as far as you needed it to. So if you take this and evaluate from 0 to 1, you do get the approximation of 0.4864. So again, no one's going to say this is an easier method or more efficient method, but in terms of the actual integration itself, you went from something that you're really going to have to work hard on to something that the actual integration process is now simplified back down to adding 1 and dividing all the way through. So it is a nice option for certain integrals. All right, so again, we'll take a look at another problem here using those power series expansions, in this case for tangent. Now, tangent's not one that we know, so we can figure it out. We know that tangent of x is going to be the same thing as sine of x divided by cosine of x. So I'm going to use some polynomial long division to come up with the expansion for tangent of x. Okay, so in doing this, I'm going to have my sine divided by cosine. So my sine expansion was the x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial. And I'm dividing it by the cosine. The cosine, which would have been the 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus, and however far out you wanted to go. Okay, so the process is always the same. What times x is, or what times 1 is going to give you the x? So we've got the x to go on top, and as I run that back through now right here, that's going to give me an x minus an x cubed over 2 factorial plus x to the 5th over 4 factorial minus x to the 7th over 6 factorial, and then so on. Now we don't want to forget, we want to subtract this. So as I subtract it now, conveniently and as planned, these go away. And now we just want to add vertically. It's been organized nice and neat to where you have your x cubes here, your x to the 5th and 7th. Now when you combine these, you will need an LCD, so take that into consideration. All right, so 3 factorial would be the 6, 2 factorial would be the 2, 5 factorial is the 120, et cetera, et cetera. So you will want to be careful on those, and feel free to use a calculator. Some of these numbers get a little bit big. But either way, in doing so, that's going to give us an x, let's use a blue, x cubed over 3 minus x to the 5th over 30, and then plus x to the 7th over 840. And now we're ready for another iteration. What times 1 is going to give us x cubed over 3? Well, naturally, x cubed over 3. So we've got plus x cubed over 3. And now as I take this guy and run it all the way through, that is going to give me the x cubed over 3 minus x to the 5th over 6 plus x to the 7th over 72. And then that would continue on. Much like the last iteration, we want to make sure to subtract. And in doing so, these guys right here go away as promised. And then we have our 2x to the 5th over 15 minus 4x to the 7th over 315 plus whatever. So if we were to continue, once again, what times 1 would give us the 2x to the 5th over 15? It would be the plus 2x to the 5th over 15. Now, generally speaking, when it comes to these types of problems, I usually ask for the first 3 non-zero terms. So first 3 non-zero terms, that would be this right here. And again, depending on the problem, you could always decide how much further out you needed to go. But this guy right here is what we're going to be using now for that tangent up here. So I'm going to go ahead and slide the screen down a little bit and replace that for our problem. So for our actual problem now, we're going to have the limit as x goes to 0. That tangent that I came up with, which was x plus x cubed over 3 plus 2x to the 5th over 15. And if we needed more, we could always go get more. And then the minus x over x cubed. So again, I just replaced the tangent here with this guy. Then we have the minus x over x cubed. So the minus x over x cubed. All right, so let's see what happens now. Well, it looks like the x and the negative x go away. So really we just have this stuff in here that's left over. I'll go ahead and I'll take the x cubed and divide up into those terms. And in this case, it looks like we were safe in only going out as far as we did, because that's going to be a 1/3 plus 2/15 x squared plus a bunch of other stuff. But you'll notice, had I continued over here and plugged it in here, all of these would have x's in it still, in which case as the limit goes off to 0, these would have all zeroed out. So it leaves us with the final answer of 1/3. So again, I hope you guys are seeing this and you're not thinking, well, this is far less efficient than just actually computing the limit. I'm not going to disagree with that. It totally depends on the limit, totally depends the context of the problem. My goal here was to show you that we can come up with these expansions, and in doing so, it does make for the elementary computation of a limit or an integral or whatever much, much easier, provided we can get through the algebra of it. Okay, so just a couple interesting examples to close out the idea of power series in the chapter.